Group 8. Today we will introduce structured grid.
The structured grid, which always appears in high-performance computing, but they also appear in various applications, and most notably in image processing for the reason that the images are the most naturally expressed in 2D mesh, and they are also higher dimensional images as well. And our presentation is about how do we parallelize operations that live naturally on 1D, 2D, or higher dimensional meshes. The model here we're going to use to illustrate parallelization techniques that apply much more broadly is going to be the Poisson equation. We will go through 4 algorithms to present in detail. The first one called Jacobi's method, and at each step we're just gonna take all values onto the mesh and averaging with nearest neighbors doing the same operations at every mesh point on structured grid, which is the building block for the later faster methods. And the next one is a variation on that red-black SOR method, which is Jacobi on subsets of mesh with different mathematical coefficients. Then conjugate gradients, which is another way to solve problems. And the bottleneck is going to be averaging nearest neighbors on a mesh, but much more general. It applies a very broad set of systems of linear equations. And finally, we would get to the most optimal algorithm called multigrid, which has to operate differently in order to converge much faster, and so it requires different techniques. Here we can see the list of all algorithms. They are sorted in 2 ways. One is from slowest to fastest, and the other is from most general, using no special structure about Poisson equation, down to using all Poisson equations, which is exploited by multigrid. Here demonstrates that Jacobi in n squares and conjugate gradients and red-black SOR, which gets it down to n of the 3 halves, and finally get down to the lower bound, which is constant amount of work for unknown, is n in sequential case.
To solve the Poisson equation, we need to know the neighbor's value, and with this neighbor's value, we can calculate the weighted average on each stencil. We can generalize the Poisson equation and reduce to sparse matrix vector multiplied by t, and each value of stencils can be updated independently. And we will implement the Jacobi's method by sequential computation. And in this way, we can easily understand the Jacobi's method. And if we want to improve the efficiency and improve the computation intensity, we can use parallel computation to implement the Jacobi's method. The naive solution is to write a row into fast memory, and we can calculate a weighted average on each stencil from its neighbors. But the fast memory is not big enough to store a row, so we need to find another way to solve this equation. And in sequential computation, we can reshape these stencils into trapezoid shape, so that the fast memory is capable to accommodate enough stencils. And in parallel computation, we need to care about the communication with each processor. So we will see the stencils in the boundary area in each processor. It can generate an overlap area, And in the overlap area, two processors will have the same arithmetic operations, but it doesn't matter because the bottleneck is limited by communication. So as long as the communication is not very high, we can make the impact from the redundancy calculation from two processors.
There are some improvements to Jacobi method. Similar as Jacobi, these improvements will also compute based on linear combination of neighbors, but the differences are mainly in two ways. First, the improvements use most recent values of u that are available to get a more accurate outcome. Second, update of value of u n plus 1 by adding multiple correction of the adjustment. The first update algorithm is called Gauss-Seidel. This algorithm uses the update part of value instead of original value in order to get a more accurate outcome. This is a strictly sequential algorithm, updating from left to right, from top to bottom. Now we want to choose an order that has more parallel. Instead of going row-wide, we divide nodes into two sets, black and red in this circumstance. At this point, all nodes of black are surrounded by red nodes, and all red nodes are surrounded by black nodes. First, we can update black nodes with red nodes surrounded by them. Then, we can update red nodes with updated black nodes surrounded by them. For the ideal model, this algorithm works fine, but for more complicated situation, we need more colors to make sure the neighbor of each color is different. So for the red-black model, the speed is twice as much as Jacobi, but there's twice as much as parallel steps. To further improve the algorithm, a factor w greater than 1 is added to the correction, so it will move further. It is called successive over-relaxation, and this will reduce the parallel steps significantly.
Then we will talk about conjugate gradient algorithm.
So for conjugate gradient algorithm, there's a loop which you repeat until the error called rho becomes small enough. It's basically doing gradient descent measure of the residual ax minus b. That's why it's called gradient algorithm. The bottleneck of the loop is the line of sparse-matrix-vector-multiply, or the stencil operation. This is where all times is spent. This algorithm converges in the same number of steps as SOR, but it applies much more generally.
Another algorithm we are going to talk about is multigrid. The idea of multigrid is to use approximation to get an approximate solution. Jacobi SOR conjugate gradient average of their nearest neighbors, thus information can only be moved one grid cell per iteration. If we want to converge in a constant amount of time, we can't just talk to the nearest neighbors. We need to communicate with more distant match points. A multigrid is a divide and conquer algorithm for solving the discrete Poisson equation. The basic idea is to use a cross approximation of a problem to approximate its solution, and recursively using a yet closer approximation of the cross problem. For example, consider an n by n grid. First, the algorithm obtains an initial solution for an n by n grid by using an n over 2 by n over 2 grid as an approximation, taking every other grid problem from the n by n grid. The crosser n over 2 by n over 2 grid is in turn approximated by an n over 4 by n over 4 grid, and so on recursively. The recursion can help get the complexity down asymptotically.
To break down the algorithm, we consider the basic algorithm multigrid V-cycle. In this basic algorithm, we start with a problem on the fine grid and approximate the high frequency in the fine grid problem. With a problem on the next crosser grid and solve the crosser problem recursively. We then map the cross solution back to the fine grid, subtract the correction computed on the cross grid from the fine grid solutions and improve the solution. This basic algorithm is called V-cycle because if we draw it schematically in space, it looks like this image on the right. The ultimate multigrid algorithm uses the multigrid V-cycle algorithm we just described as a building block. It solves the simplest problems and given the solution of the cross problems map to a starting guess for the next final problem. And it solves the final problems using the multigrid V-cycle with this starting guess.
So how do we parallelize a 2D multigrid? So here we have a 32 by 32 fine mesh, and we simply spread it on a grid of 4 by 4 processors. There are 5 levels of calculations. Unknown mesh points in each level are labeled by the level index. In each level, each processor is responsible for calculating unknowns within its grid. However, as the level goes down and the mesh gets coarser, the number of unknowns decreases. Some processors even become idle at the coarsest mesh. In terms of communication, each processor needs to communicate with 4 neighboring processors, but the number of mesh points passed between them decreases as the mesh gets coarser. This parallelization results in time complexity as listed in the table.
Here we have 3 discussion questions. The first one is what improvement we made for Gauss-Seidel algorithm. The second one is what is the main difference between multigrid and Jacobi SOR-CG or any other sparse matrix-vector-multiply-based algorithm. And the last one is that what determines the success or failure of multigrid.